Hello everyone, today we are going to talk about virial identities in relativistic gravity. Now, in physics, independently on the complexity of the system, there is a conserved quantity, which is the total energy, and this is always conserved, and can be seen as a sum of the potential energy, U, and the kinetic energy, T. However, a deeper relation between these energies also exists, which is known as the virial identity, which relates the average kinetic energy with minus one half of the average potential energy. And this is known as the virial identity, and is always obeyed. However, the concept of energy in general relativity is not trivial, and the previous relation cannot be directly applied. So we need to find out some other way to compute the virial identity in general relativity. So for this, we are going to first introduce virial entities, and this is important. We'll show a recipe for the computation, some applications, in particular spherical symmetry and axial symmetry, where we are going to see the importance of the Gibbon-Socking-York term, which is a boundary term. We'll show a master-like identity and the conclusion. So, let us introduce. Now, the virial theorem or the virial identity relates the average kinetic energy with the average potential energy. And this is very important, especially for very complex systems of particles, where the average kinetic energy is very hard to compute. And this is interesting because for particles of systems of particles, this relates to the temperature. And so, the virial theorem allows us to compute the temperature or the average kinetic energy or very complicated systems just by knowing the potential energy, which in other ways is related to the position of each particle. However, this theorem has also found application in other areas, and of particular interest for us is the case of the presence of an additional matter contribution to the universe. So, what we are interested is in integral identities that are virial-like, but in field theory rather than particle mechanics. And these are obtained through a scaling argument, which is known as Derik's scaling argument. And very importantly, they are computed independently from the equations of motion. This so far has only been applicable to stationary spacetimes, and what we want is to present an approach for curved spacetimes. But before that, it's very important for us to decide or to understand what is the importance of these identities. And for strong gravity, it's mainly 5. These identities can be used to establish no-hair theorems, where they rule out the existence of additional degrees of freedom, or hair for black holes. They can also be used to rule out solitonic solutions, which these are known as no-go theorems, an example of which we are going to see ahead. They can also be used to simplify the model or requirements. So imagine that you have a system that you don't know anything about, a new model, and you don't know how your function depends on the coordinates. So you can just put all the dependence and the coordinates for a given field. You compute the identity and then use it to rule out the dependence on some functions, effectively simplifying your model. Probably the most well-known use of this identity is as numerical accuracy. Since these results are independent from the equations of motion, these can be used to study the numerical accuracy of your numerical computation, since these are independent from the previous computation and gives a kind of physical test from your results. And probably the first one to use as data analysis, especially with a particular interest on the rotational curves of galaxies. This was the first use of such identities, where due to the additional kinetic energy on the rotational curves of galaxies, it was inferred the presence of an additional matter field, which we now call dark matter. So in this case, it's all opposed to the case of particle systems, where in this case we use the kinetic energy to obtain the potential energy. So, let us study our recipe. First, we need to show the ingredients. We will consider the action of your model, a metric and matter ansatz, and for the case of gravity, the Gibbon-Hawking-York term. For the material, we'll consider Derrick scaling argument, Hamilton's principle, and with all good recipes, a lot of love and patience. And our recipe goes as follows. First, you write your model by writing the action. You introduce your metric and matter ansatz, which in this case we are generally consider x. And then we compute the effective Lagrangian. Basically, we integrate all the independent variables of your Lagrangian. With this, you obtain your effective action, and then you perform the following scaling. R goes to lambda r. This means that x goes to x of lambda, and the derivative goes as 1 over lambda. We also have to scale the Jacobian, and then obtain an effective action that is dependent on lambda. Then we apply Hamilton's principle, which states that the variation of the action with respect to any of its parameters is equal to 0, and we set lambda equals to 1 to recover the original model. And this is known as a virial identity. This will give a relation between all the components that must be obeyed. But let us study for some cases. Let us start with spherical symmetry, which is the easiest case. In particular, let us follow Derrick's argument, which works for a real scalar field in flat spacetime, so no gravity. Derrick's argument was originally proposed for a real scalar field that is under a self-interaction potential U. We can divide the action in three terms: a time dependence, a space-like dependence of the field, and a potential. However, let us consider a time-independent scalar field. To obtain the identity, we consider the radial transformation, r goes to lambda r, which is basically equivalent to changing the energy of the field. This means that phi of lambda goes to phi of lambda r, the derivative goes as 1 over lambda, and the r goes to lambda dr. Then, applying the variation of the action, we obtain the following identity, where we can see that the left-hand side is always positive, and hence, since we are only interested in non-negative self-interaction potentials, this relation can never be obeyed, and hence, solitonic objects or objects made by this kind of model are impossible. This is known as a no-go theorem. However, a way to circumvent such argument is to include a time dependence, where we consider a exponential time dependent, an harmonic time dependence, just because it makes our stress energy tensor time independent. Since now the field is complex, we have to change slightly the action. However, after applying our recipe, we obtain the following identity. And in this case, we can see that the non-negative self-interaction potential is being counterbalanced by the dispersiveness of the field that comes from the time dependence. And this creates objects that are self-consistent and are known as cuboids. However, when we include gravity, the gravitational contribution of the action must include an additional term. It should be computed by the usual Einstein-Hilbert action, which is just a Ricci scalar, plus a boundary term, which is the Gibbon-Hawking-York term, which comes from the fact that the system has two boundaries and has a total derivative. And is computed by the difference between the extrinsic curvature of both surfaces, boundaries, and K0, which is extrinsic curvature of the flat spacetime, which is just coordinate dependent. And this boundary term is needed since the gravitational Lagrangian density contains second-order derivatives of metric tensor, as I already explained. For the gravitational action, we need to introduce a metric ansatz, and for this, let us consider a generic metric ansatz that is compatible with spherical symmetry, which contains two unknown functions, n of r and sigma of r, which are unknown functions. However, these solutions are known for a spherically symmetric black hole, in this case Schwarzschild black hole, where sigma is equal to 1. In this case, due to the appearance of an horizon, there is an additional boundary, which is the horizon, and hence the radius has to be translated to this horizon radius. This means that now the transformation of the radius will be h of r of h, which is the horizon radius, plus lambda r minus rh. With this, we are able to compute the Gibbon-Hawking-York contribution, which is not very complicated, and we are able to numerically integrate it, which gives minus 4m. And this is exactly the same as the one from the Ricci contribution. However, since these terms are highly dependent on the metric ansatz, it is possible to consider another parameterization for the metric. In this case, for the n function, let us consider the parameterization that considers the Misner-Sharp mass function, which is again an unknown. The gravitational action will be the same as before. However, for this case, if you compute the previous Gibbon-Hawking-York term, you will see that this is equal to 0. And hence, the contribution only comes from the Einstein-Hilbert, and we can see that it gives for the integral of sigma m prime. However, the Ricci contribution will come as 1 over lambda, and hence, when we do the transformation, we can see that both variations cancel, and hence the gravitational contribution is equal to 0. And this means that then, when we compute the virial identity, it will only be come from matter field contributions, no gravitational part. And this extremely simplifies our computation. And so, this will be our preferential metric for future computations. So, let us consider now a black hole example. Let us consider previously established metric ansatz. And let us consider a simple Einstein-Maxwell scalar model, where we have a scalar field, we have a Reisnerson black hole, first of all, electrically charged black hole, and then we have a real scalar field that is non-minimally coupled to the Maxwell invariant through a coupling function f of phi. This is known to originate solutions of scalarized black holes, where you can have a black hole that is surrounded by a scalar field, and you can imagine this as having a marble surrounded by cotton cloud. While before, in the case of the cube balls, you only have a cotton cloud. In this case, since we are using the previous metric parameterization, we know that the gravitational contribution is trivial, and hence we can only consider the matter contribution. If we apply our recipe, we obtain the following identity, where it can be shown that the left-hand side is always positive, and hence the solution can only exist in the presence of an electrical charge. And this creates scalarized black holes. Additionally, let us consider now the axial symmetry. And for this case, let us start again with the simplest case, flat spacetime and the complex scalar field. And again, we are only considering non-negative self-interaction potentials. In this case, now we have an harmonic time and azimuthal dependence due to the axial symmetry of the system, and the scalar field amplitude phi is now dependent of both radius and polar coordinate. Then, if we apply our recipe, which is always only to the radial coordinate, we obtain the following identity, which in this case is a little bit more complex due to the additional dependence on theta. In fact, notice that now we cannot integrate directly the angular coordinate, and we need to integrate it at the end. However, we can still see that the non-negative self-interaction potential is only being counterbalanced by the dispersiveness of the scalar field. And again, this creates objects that are known as cuballs, and in this case these are spinning cuballs. So imagine your cotton cloud is spinning and is donut shape. Let us consider now the gravitational action, which is computed as normal, and if we apply a recipe, we should obtain a relation which relates the virial identity contribution from the Einstein-Hilbert is equal to the Gibbon-Hawking-York term. Let us start then to apply this for a well-known result, which is the Kerr black hole. For this, again, we have to consider a metric ansatz, and we will consider a generic metric ansatz that is compatible with axial symmetry. And in this case, it contains 4 unknown functions. Let us start by considering the Gibbon-Hawking-York term. In this case, we know the asymptotic behavior of the functions goes as Ct of R, which is just a constant that is related with mass and spin of the black hole. And in this case, we are able to obtain both extrinsic curvatures, and they are not very complicated, and this will give a Gibbon-Hawking-York term equals to 4Ct. If we consider Einstein-Hilbert term, it is, in this case, it will be very complicated. However, we are still being able to integrate it algebraically, and this gives 4Ct again, which is exactly the same as before. And thence our identity and model works. Let us consider now a model which contains a matter contribution. In this case, let us consider a black hole, a spinning black hole, which is interacting with a spinning cue ball. In this case, we have this complex scalar field and the spinning black hole, and we are expecting to obtain some kind of solution where the black hole is synchronized with the spinning cue ball, or the boson star, which is the case of the cue ball with gravity. If we apply our variation to the matter part, we obtain a relatively simple relation. However, you can see now that due to the additional spinning contribution and the gravitational part, the relation is too complex to obtain any interesting behavior. So we cannot infer any conclusion just from this identity. In addition, we can also do to the gravitational contribution. However, notice that now, due to the fact that all the functions are numerical, we cannot integrate it readily, and this gives a very complicated virial contribution from the Ricci scalar. In fact, it is a mess. However, since from what we observe in spherical symmetry, since the gravitational contribution is only metric dependent, it is reasonable to assume that there is a convenient parameterization for the metric dependence that trivializes the gravitational contribution. And so, if we introduce the following metric ansatz, we aim to observe that the gravitational contribution is equal to 0. The gravitational action is given the same, which is a relation between the two contributions of the Ricci and the Gibbon-Hawking-York term for the virial identity, and we'll consider again the Kerr black hole. Let us start by the Gibbon-Hawking-York term again, which in this case is a slightly more complicated. However, it is a valuable result, because now, when you compute the Gibbon-Hawking-York term, it is 0. In fact, it is 0 even before the Rayleigh integration, which seems to indicate that this metric parameterization makes the gravitational contribution equals to 0 independently on the spacetime that we are considering. We can do the same for the Einstein-Hilbert case, and we can see that the Ricci scalar is again very complicated. However, notice that for every derivative of the functions, there is always a r minus rh term multiplying by it. This means that the Ricci contribution can be seen as 1 over lambda, and thence when you do the transformation, this will be a constant, and after the variation, the Ricci contribution will be equal to 0. And thence this metric is much more easily to obtain and to compute our identities. For this, let us consider the model as before, the spinning complex scalar field around our black hole. And in this case, since we are using the convenient metric parameterization, the gravitational contribution is trivial. And this will give a simpler relation between the matter contributions. However, these are still much more complicated than the ones from the spherical symmetry, and no insight or no new knowledge is able to obtain from this identity. At last, let us consider some toppings. First, from the first Kerr metric or spinning metric, we are able to obtain the following identity, which can be cast, since the matter contribution can be cast just as a sum of the stress energy tensor parameters, and we know that the Einstein-Hilbert the Einstein tensor should be obeyed, we can obtain the following master identity, which must be obeyed. And observe, however, this is a master-like identity, since the Einstein tensor terms have to be multiplied by some part of the metric parameters. So it's not that generic. If we consider our convenient gauge, since the gravitational contribution is still zero, the master identity can be cast as just the stress energy tensor contributions. However, there are still some metric parameterization component. And this can be seen as a generalization of desert argument or desert theorem, which is just a sum of pressures. And this theorem was first used to obtain the dark matter presence in the rotational curves of galaxies. At last, there are some secondary relations. For this, let us consider the initial axial metric gauge, which depends on the exponential of f of 0. If we compute the identity, we can see that the gibbon Hawking-York contribution is lambda function independent. This means that then we can scale the Ricci contribution by lambda and perform two different lambda parameterizations. For example, we can consider one lambda and one lambda over r. And since the gibbon Hawking-York term is independent, their difference should be equal to 0. And this gives a secondary relation that can also be used to put constraints of lambda, or to start from one metric general parameterization and go to another, such a way that it makes our parameterization simpler. Finally, for higher curvature corrections, while let us consider Einstein scalar Gauss-Bonnet, and in this case the Gauss-Bonnet is just a sum of second order curvature corrections, and the gravitational action will be equal to the Einstein-Hilbert, the Gauss-Bonnet, and the Gibbons-Hawking-York, where the Gibbons-Hawking-York term now will also have to contain second order curvature corrections, which can be just cast as the variation of the curvature corrections as a function of each curvature parameter. To conclude, in this work we presented a generic recipe to compute Virial identities in field theory. We have observed that the Gibbons-Hawking-York term is required due to the presence of second order derivatives of the metric field. However, since the gravitational contribution is dependent on the metric parameterization, we have noticed that for a generic metric, these relations are too complex. However, there is always a special case that trivializes the gravitational contribution and makes our identity solely matter dependent. We have also been able to recast our identities in a combination of the equations of motion, which created a master-like form of the identity. At last, we have observed that the Virial identities are a helpful tool that can be used to have a better insight into the models. With this, thank you.